This formula for the geometric series is rather ugly. To see that this is really, the left side is really the geometric series, think about when k is 1. K is 1, it gives you a times r to the 0th power. Anything to the 0th power is 1. 1 times a is just a. But then when k becomes 2, 2 minus 1 is 1, so you get ar. When k becomes 3, 3 minus 1 is 2, so you get ar squared. So you see that this r goes up, 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 until it reaches n. When k is n, you get a r to the n minus 1. And as you can see, every time you proceed to the next one, it's multiplied by r. So indeed, this is a geometric series, and this would be the nth term of the geometric series, and its formula is this thing. Now, the proof for this is not that hard. In fact, if you forget the formula for this, you can just redo the proof, which is just set it equal to s, and then you multiply by r, so that you get ar plus ar squared. Everything would be multiplied by r, so it's like that, right? And then what you do is you subtract the two. S minus rs is what you get on this side. On this side, everything goes away except these two. So you have a minus ar to the nth power, so that if you factor a on the left side, it's a1 minus r to the nth power. On the right side, if you factor s, it's 1 minus r. And therefore, if you solve for s, you get s equals to a times 1 minus r to the nth power over 1 minus r, which, by the way, is the preferred formula when r is less than 1 and bigger than -1. But if r is a value that's bigger than 1, you probably want this to be positive, so you multiply by -1 top and bottom, and the result is that you get a times -1 plus r to the nth. -1 times 1 minus r would be -1 plus r. When you multiply, you don't distribute. You only have to multiply to one of them, so I just multiply -1 to this one, so that's what I get. And if you change the order, this will be exactly this formula that you see there. So the formula itself is not that hard to prove, but I also want to link this with another well-known factoring theorem, and those two should be thought together, because if you do, then it becomes a lot easier to recognize this, and this will it will make more sense. Okay, so even though you think you've now learned this formula and you figured out why it does work, please bear with me and try to follow my reasoning. Okay, so the first thing I want to show you is the formula for the factor of x cubed minus 1. You probably know that this factors as x minus 1 times x squared plus x plus 1. If you don't, you should know this. And this is actually true for, say, x to the 9th power. You know, x to the 9th power minus 1 is again x minus 1. But then to get the 9th power, you need x to the 8th power times x to create the x to the 9th power, right? And you get 7th, 6th, all the way up till x plus 1. Now, to see why this pattern always is true, all you have to do is multiply the x's and -1. So if you multiply by x, you get x to the 9th plus x to the 8th, x to the 7th, and then x times x is x squared, x times 1 is x, and then you subtract x to the 8 plus x to the 7 all the way up to x plus 1, because -1 is just multiplied to this thing, right? But then you can see that the common things will cancel out, so everything will cancel, and at the end of the day, you're just going to get x 9th minus 1. That's why if you have x to the nth minus 1, it will always have a factor of x minus 1, and then this will go with the n minus 1, n minus 2, all the way up till x plus 1. Okay? So just look at this, and because this is actually a pretty important factoring formula, and even if you never see this on an easier exam, this is actually something that everyone is expected to know. So when n is 3, you get this more well-known formula. So you should know this, okay? To further investigate this, here's another way to look at this. So how would you factor x to the n minus 1? Well, if you call this f of x, then f of 1 is 1 to the nth power minus 1 equals to 1 minus 1 equal to 0. And there is something called the factor theorem, which says that if f of a is 0, then x minus a is a factor of the polynomial f of x. So if f of x is a polynomial, then when you plug in some value and you get 0, that means that x minus that value is a factor of x. And if you apply this factor theorem, you know that x to the n minus 1 must have x minus 1 as a factor. Now, if it does have x minus 1 as a factor, then how would you figure out this other one? Well, you just have to divide this by that, and to do that you would use something called synthetic division. Now, if you forgot synthetic division, don't worry too much about it, but if you do know synthetic division, it works like this. It's like 1, and then you get 0 x to the n minus 1, so you have a lot of zeros, and then finally you have a negative 1, right? And then you want to divide x to the n minus 1, which is represented by this one, by x minus 1, so you put in 1. You think about what makes this as 0, so you put that value here. 1 comes down as 1, and then 1 times 1 gives you 1, add, you get 1, 1 times 1, you get 1, you add and you get 1. So you always get 1, except that here, negative 1 plus 1 gives you 0, but we know that this last one is the remainder, which means if remainder is 0, then this x minus 1 indeed is a factor. And then if you look at this, you see that all the coefficients are 1, right? So that's why you have 1 and then x and all the way up till x to some power, but that x to some power times x has to be x to the n, so this has to be one less power than x. It should be 1 less power than x to the n. So that's why you have such a formula. Okay, so by now, hopefully you understood that this is a formula that does appear a lot. Now let's try to use this for adding the geometric series, which is a plus ar squared all the way up till ar to the n minus 1. So here's what we're going to do. For this geometric series, we're going to factor the a out. And then what you want to do is we want to turn this into fraction by multiplying by r minus 1 on top and r minus 1 on the bottom. And you should recognize that if this r was instead of x, then that's exactly the factor form for x to the nth power minus 1, right? So I'm saying that if you take this x to the n minus 1 equals to x minus 1 times x to the n minus 1 plus all the way up till x plus 1, and then you replace these x's by r, you get r to the n minus 1 equals to r minus 1 and r to the n minus 1 plus all the way up till r plus 1. And this is exactly this one. This is exactly this one. And therefore, if you multiply them, you're going to get r to the n minus 1 over r minus 1. Okay? So if you can do all this in your head. So try to start from here without looking at this. Try to recreate the steps going from here until here purely in your head. Then you'll see that not only it's possible, in addition to that, this formula will just make sense. Of course, it has to be that way. And often, see, what I'm providing you is just an alternative way of proving this formula, but you get something in bonus. This formula, the outcome, looks a lot more natural than going by the first proof I gave you. So try to redo this in your mind, and you'll have a lot of benefit from that. Now I want to conclude this one with the infinite geometric series. So we will go by this a plus ar plus ar squared plus ar to the n minus 1 equals to a times 1 minus r to the n divided by 1 minus r. The one where these two terms are flipped, right? So start from here and think about the following question. If I go a whole step, then I go half step, then I go another half step, 1/4, another half step, which is 1/8. You keep moving by halves. That means you keep moving forward somehow, right? If I do this infinitely many times, would I go to infinity or would it stop? That would be a question, right? And if it does stop, where does it stop? So let's think about that. And it's like this. It's 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and so on and so on. But that's a geometric series, right? It's like 1 plus 1 times 1/2 plus 1 times 1/2 squared plus 1 times 1/2 cubed and so on and so on. And this is like a geometric series where n is infinity, right? This never stops, so that's like infinity. So you can use this formula, but with n being infinity, so you get a, the first one is 1 minus, and r is 1/2, infinity, divided by 1 minus 1/2. But if you take 1/2 and you take half of half of half of half of half, what happens? This just becomes smaller and smaller, right? So this, if you do this to infinity, this will just become 0. And the result is that you get just 1 minus 0, which is 1 times 1 minus 0, which is just 1 on top. 1 minus 1/2 is 1/2. So you get 1 divided by 1/2. And what is that? That's the same as 1 times 2 over 1. You flip this and multiply, and which is just 2. So if you do this, you actually get terminated at 2 feet. So if this was like 1 foot, and then half foot, quarter foot, and then so on and so on, then if you keep adding them, you just get 2 from this. So such a thinking is called infinite geometric series. And the formula for infinite geometric series goes like this. If you have r which is less than 1 and bigger than -1, then taking r to the infinity just becomes 0, right? You just take half of half of half of half, we get 0. Same thing if it was like 1/3, 1/3, 1/3. A third of a third of a third would just keeps shrinking and you get 0. So this just goes away, and the formula is that you have a plus ar plus ar squared. And if this geometric series never ends, then this becomes a divided by 1 minus r, if r is between 1 and -1. Now if r is not these, like if r is like 2, then it just, if it's like 1 plus 2 plus 4 plus 8 plus 16, it just goes to infinity. So you don't get a value, but if your r value is between -1 and 1, then the infinite geometric series can be evaluated as a over 1 minus r.